On November 12, 2025, in the silent, cold expanse between Earth and the Sun, something that was never supposed to be there in the first place began to tear itself apart. Astronomers designated it C2025 K1 Atlas, a name it shared with another, earlier visitor that had already shaken the foundations of what we know about our solar system. Just months before, an object named 3I Atlas had barreled into our neighborhood from the blackness of interstellar space. Now, its namesake was staging a performance even more bizarre, fragmenting in ways that defied the gentle tug of gravity alone, glowing with colors comets aren't supposed to glow. Two objects, discovered by the same survey in the same year, both acting in impossible ways. Is it a coincidence? Perhaps. But the data, relentless and cold, keeps getting stranger. Stay with me through this investigation, because once we assemble all the pieces of this cosmic puzzle, you will understand why some of the world's leading scientists aren't sleeping well anymore. If you're as captivated by this mystery as I am, make sure you subscribe to this channel. I want this community to be the first to know. Let me know in the comments where in the world you're tuning in from right now, what time it is there, and what your gut feeling is about how much we're actually being told. Thank you for being part of this search for answers. Now let's begin with the event that started it all, the breakup that should never have happened. On that fateful night of November 12, 2025, astronomer Gianluca Marsi pointed the powerful instruments of the Virtual Telescope project toward a faint, unassuming smudge of light. His target was comet C2025 K1 Atlas, discovered 6 months earlier by the Atlas Survey Network in Chile. Marsi expected a routine observation session, tracking a comet as it rounded the Sun and began its long journey back to the outer darkness. What he captured instead was something astronomers almost never witness in real time: the violent death of a comet. The images from November 12th and the following day told a story of chaos and precision. The comet's nucleus, its solid heart, was splitting, not into a vague cloud, but into multiple distinct, sharp fragments. Each piece was now a miniature comet in its own right, trailing its own ghostly coma of gas and dust. But beneath the largest leading fragment, something else was happening. A bright, narrow plume extended outward, not like a diffuse puff of smoke, but like a searchlight beam, persistent, directional, and unnervingly structured. It looked less like passive debris and more like something was actively venting. Something under immense pressure was finally releasing itself into the vacuum. You might think comets fragment all the time, and you'd be right. They're fragile, cosmic, dirty snowballs, baked by solar radiation, spun by uneven heating, and shaken apart by thermal stress. But K1's behavior was different in its speed, its structure, and its timing. Most cometary breakups are slow, gradual affairs over weeks or months, the nucleus shedding layers like a rotting onion. Others explode in a single dramatic burst, scattering their remains into an untrackable cloud. K1 did neither. It split rapidly, decisively, into multiple, trackable pieces, arranged in what appeared to be a deliberate line. Each fragment was distinct enough for astronomers to monitor separately. The most perplexing clue was the timing. The comet had already survived its closest approach to the Sun just days earlier. Its perihelion brought it within 0.334 astronomical units, closer than the orbit of Mercury, a distance that vaporizes most comets and stresses any structure to its absolute limit. K1 made it through. It rounded the inferno of the Sun, climbed back outward, and then, as if on a silent internal timer, it began to disintegrate. Scientists call this behavior anomalous not because it's impossible, but because it is profoundly unexpected. The comet should have broken during perihelion, when the stellar and gravitational stresses were at their maximum, or it should have held together afterward if its structure was strong enough. Instead, it waited. It survived the worst the Sun could throw at it, only to fall apart in the relative calm of the days that followed. The question is, why? And this is precisely where the story twists into something far stranger. K1 Atlas shares more than just a name with that other headline-making object from 2025. In July of that year, astronomers confirmed the detection of the third interstellar object ever discovered, 3I Atlas. Same survey network, same naming convention, both appearing within months of each other, and both exhibiting behaviors that make scientists deeply uncomfortable with simple textbook explanations. The coincidence raised immediate and unsettling questions. Could these two objects be related? Could K1, despite being classified as a long-period comet from our own Oort cloud, actually be another visitor from the vastness of interstellar space? Or perhaps a fragment of a larger, unknown body that arrived earlier, broken apart before anyone noticed, seeding our inner solar system with pieces that are only now revealing their true, bizarre nature. The virtual telescope images show K1's fragments suspended in the blackness, each a new world trailing its own faint tail, that bright plume still burning beneath the leader. Massey's observations captured not just a breakup, but a transformation, a moment when a single celestial body ceased being one thing and became several. The data would take weeks to fully analyse, but even in those first few hours, the astronomers watching their screens knew, with a chilling certainty, that they were witnessing something significant, something that would change everything. No one missed it this time. Within a mere 24 hours of the fragmentation event, astronomers across the globe who were tracking the pieces of K1 Atlas noticed something that should have been impossible to detect so quickly. The fragments were drifting. This wasn't just the expected separation from each other in the aftermath of a breakup. This was a deviation from the very trajectories that gravity alone would dictate. There were subtle offsets, small accelerations, tiny nudges that had no business being there. It was the kind of motion that makes orbital mechanics specialists, the people who chart the paths of celestial bodies with mathematical precision, deeply uncomfortable. Now, it's well known that comets don't follow perfect gravitational paths. When a comet heats up, its ice vaporizes, and jets of gas erupt from its surface, pushing the nucleus in directions that Newton's laws alone can't predict. These non-gravitational forces are well documented, carefully modelled, and are usually small enough to be treated as minor perturbations. But they complicate everything. Every trajectory calculation must account for this outgassing, for the comet's spin, for asymmetric heating, for the momentum transfer of millions of tons of gas and dust streaming off into space. The history of interstellar objects is littered with persistent motion anomalies. The first confirmed interstellar visitor, 1I Oumuamua in 2017, accelerated away from the Sun faster than gravity alone could explain, leading scientists to propose outgassing, even though no visible coma was detected. The second, 2I Borisov in 2019, showed more typical cometary behaviour, but still had trajectory quirks that required careful modelling. And 3I Atlas, the third interstellar visitor confirmed in July 2025, exhibited motion patterns that defied simple explanation. This time, however, astronomers were ready. K1's discovery back in May meant there had been months of preparation, precise tracking, dense observational coverage, with multiple facilities monitoring its progress. When the fragmentation occurred in November, the world's instruments were already pointed at the comet. The Virtual Telescope Project, the Comet Observation Database maintained by dedicated amateur astronomers worldwide, and several professional observatories, all captured data within hours of the split. What this tracking data revealed was fragment separation speeds that were completely inconsistent with a simple breakup scenario. When a comet nucleus fractures, you expect the pieces to drift apart slowly, carried by the object's residual rotation and minor outgassing. The fragments should move in predictable arcs determined by their initial velocities and the Sun's overpowering gravity. K1's fragments moved differently. They diverged at angles that suggested ongoing acceleration, not just the momentum from the initial split. Measured drift rates reached several meters per second within just 48 hours. Velocities far too high to explain through passive separation alone. The angles of divergence didn't match what the models predicted for a typical cloud of dust and gas, expanding from a fractured nucleus. Something was actively pushing the fragments, giving them momentum beyond what the breakup itself could possibly provide. Within conventional comet science, two explanations exist. First, asymmetric outgassing. If one fragment has an active jet and another doesn't, they will accelerate differently. Second, structural shedding. If the breakup exposed fresh, volatile-rich layers, sudden sublimation could produce thrust. Both mechanisms are real, both have been observed, but the sheer speed at which K1's fragments diverged and the persistence of this effect over multiple days points to something far more potent than casual outgassing. Only a tiny percentage of comets show measurable non-gravitational accelerations strong enough to significantly alter their orbits over short periods. Most outgassing effects accumulate slowly, becoming obvious only over weeks or months of careful tracking. K1's drift appeared fast, obvious, and immediate. Within just 2 days, the offsets were so large that amateur astronomers with modest backyard telescopes could see with their own eyes that the fragments were not where simple gravity insisted they should be. Specialists in orbital dynamics now face an immense challenge. They need to model not just one object, but multiple fragments, each potentially outgassing at different rates, each with a different surface area and volatile content, each tumbling at a different rotation rate. The computational complexity multiplies with every fragment, and the uncertainties compound rapidly. But even the most generous estimates of normal outgassing can't fully account for what the observations so clearly show. This rapid separation forces us to ask a more profound question. Could it hint at something beyond typical cometary behavior? Could it suggest an internal structure under unimaginable stress, releasing its stored energy in ways we have never seen before? Or could it indicate that K1's composition includes exotic materials that sublimate more violently than water ice, driving faster, more dramatic acceleration? The motion data also reveals secrets about the fragment spacing itself. If you measure the distances between the pieces and track how they change over time, you can begin to infer properties of the original nucleus. The rotation rate, for instance, profoundly affects how fragments separate. A fast-spinning nucleus sheds material along its equator, flinging pieces outward like a spinning top shedding droplets of water. A slow spinner breaks more symmetrically. K1's fragments suggest a rotation period of several hours, typical for comets. But the spacing also hints at deep structural divisions within the nucleus, layers or boundaries where the material was inherently weaker. External forces beyond outgassing seem unlikely. Solar radiation pressure affects tiny dust particles, not kilometre-scale fragments. Magnetic fields in space are far too weak to move icy bodies. Gravitational interactions with planets are negligible at K1's distance from them. Therefore, the acceleration must be coming from the comet itself, from internal processes, from the release of energy or momentum stored within its very structure. This is the point where straightforward science begins to edge into speculation. If K1's motion cannot be easily explained by standard comet physics, and if its chemistry is also unusual, and if its breakup pattern is also strange, then perhaps the object itself is fundamentally unusual. Maybe it's not a typical Oort cloud comet at all. Maybe its internal structure is nothing like what we expect. Maybe it's something we have never encountered before, or perhaps we have encountered it but failed to recognize it for what it was. The inevitable comparison to 3I Atlas becomes unavoidable. That object too showed motion anomalies, trajectory quirks that required careful, complex modeling to even begin to explain. Both objects were discovered by Atlas. Both exhibited non-gravitational acceleration. Both appeared within months of each other. Coincidence is the default, conservative assumption in science. Random chance produces patterns all the time. But coincidence becomes a less and less satisfying explanation when the patterns multiply and intensify. If the motion is weird, then what about the object's very composition? That is where the next, deeper layer of the mystery unfolds, because K1's chemistry turned out to be just as anomalous as its trajectory, just as difficult to force into the standard cometary framework. The spectroscopic data revealed something rare, something seen in only a handful of comets across decades of observation. And that rarity, when combined with the motion anomalies and the bizarre fragmentation pattern, begins to paint a portrait of an object that doesn't quite belong in any category we have ever created. When astronomers around the world pointed their most sensitive spectrographs at K1 Atlas, they expected to see the familiar, comforting signatures of a typical comet. Bright emission lines from carbon-based molecules, the blue-green glow of C2 and CN radicals, the standard chemical fingerprint of an icy body sublimating under the sun's relentless heat. What they found instead was an absence. The carbon was missing. Or to be more precise, it was severely depleted compared to what every typical comet shows. Carbon chain molecules are fundamental to cometary chemistry. When sunlight heats a comet's surface, its frozen compounds vaporize and break apart into simpler molecules. Carbon dioxide becomes carbon monoxide, which becomes atomic carbon. Complex organic chains fragment into smaller radicals. These excited molecules emit light at specific wavelengths, creating the colorful comas that make comets so visibly spectacular from Earth. C2 emissions produce a distinct cyan blue color. CN creates a similar hue. Together, they give most comets their characteristic blue-green appearance. K1 Atlas showed almost none of this. The spectroscopic measurements revealed carbon chain molecules at levels far below normal, so depleted that the usual telltale chemical signatures were faint or entirely absent. This trait is exceptionally rare. Across decades of comet observations, only a handful of objects have shown similar depletion. It's not completely unheard of, but it is uncommon enough that when it does appear, astronomers immediately take notice. What does this carbon depletion mean in practical terms? It means the comet's fundamental chemistry is different from the standard solar system template. It might have formed in a much colder region of space where carbon compounds froze out differently. It might have been heated and processed long ago in ways that drove off the volatile carbon before it ever entered the inner solar system. It might have a radically different dust-to-gas ratio, favouring rocky material over ices. Or it might simply be incredibly ancient, its surface layers depleted after multiple passes near the Sun, though all evidence suggests K1 was on its first inbound journey. The missing carbon affects more than just the comet's colour. It directly influences how the nucleus responds to solar heating, how quickly it outgasses, how much momentum those escaping gases transfer, and ultimately, how fragile or stable the structure remains under stress. Carbon-depleted comets tend to have unusual dust-to-gas ratios, often favouring dust, which makes them appear redder or more neutral in colour rather than blue-green. They may also fragment more easily if their internal ice content is lower, leaving behind a more porous, crumbly structure. This connects directly to the observations, as witnesses noted that K1 developed a rare golden hue after its perihelion. Most comets trend blue-green, or occasionally red from dust. A golden colour is uncommon, and it is almost certainly connected to the absence of typical carbon emissions and the resulting dominance of dust scattering sunlight. The colour is a direct message, telling us something vital about its composition, about what molecules are present and, just as importantly, which are absent, about how sunlight interacts with the coma particles in a novel way. Now we must consider 3I Atlas once again. That object's own spectroscopic analysis, largely conducted by the James Webb Space Telescope, revealed an unusually high ratio of carbon dioxide to water, far exceeding what solar system comets typically show. The detailed spectra showed CO2 dominating the outgassing, with water playing a surprisingly minor role. This bizarre chemistry suggests formation in an environment completely different from our solar system's comet-forming regions, possibly around a different type of star, where temperature and chemical gradients produced radically different ice mixtures. K1's carbon depletion and 3I's carbon dioxide excess are not identical anomalies, but they share a powerful, common theme: unusual chemistry, compositions lying far outside the normal range, signatures that force scientists to seriously question the object's origins. If both objects formed in interstellar space, or in star systems with different chemical environments, these anomalies might be expected. If they're both from our own Oort cloud, the anomalies require far more creative, and less likely, explanations. A working hypothesis beginning to circulate among some researchers is that K1 behaves more like a processed interstellar fragment than a pristine Oort cloud nucleus. Imagine a small body that formed around another star, spent millions of years travelling through the galaxy, being bombarded by cosmic rays, heated by nearby stellar flares, chemically altered by relentless radiation and micro-impacts. By the time it finally enters our solar system, its surface chemistry has been utterly modified, its volatile content permanently changed, its very structure weakened by radiation damage. Such an object would be predisposed to fragment easily, to outgas in unpredictable ways, and to show the kind of unusual spectroscopic signatures we are now seeing. Of course, caution is warranted here. Carbon depletion alone is not proof of an interstellar origin. Many solar system comets also show depletion, particularly those that have been heated or processed during the outer solar system's early chaotic period. Jupiter family comets, which orbit closer to the Sun and have been through multiple heating cycles, often show depleted volatiles. Long-period comets from the Oort cloud can also show chemical variations, depending on where in that vast cloud they formed and what perturbations sent them inward. But it is the potent combination that troubles scientists. Carbon depletion, plus unusual motion, plus organised fragmentation, plus a golden colour, plus the eerie timing connection to 3I Atlas. No single anomaly proves anything definitive, but multiple significant anomalies accumulating in one object begin to strain the most straightforward explanations to the breaking point. Each new data point adds weight to the unsettling possibility that K1 is not quite what it seems. Spectroscopy also reveals critical information about dust properties, the size distribution of particles, their composition, their optical properties. All of this affects how they scatter sunlight. K1's coma showed dust particles with size distributions skewed toward larger grains compared to typical comets. This could indicate a fragile nucleus shedding chunks rather than fine powder, or it could reflect a different formation environment where larger particles naturally dominated. The chemistry isn't just a footnote in the K1 story, it might be the master key that explains everything else. If the nucleus is truly composed of unusual ices, processed by radiation and depleted in key volatiles, then it makes perfect sense that it would fragment so easily once solar heating began. It makes sense that its outgassing would be asymmetric and unpredictable, driving the motion anomalies. It makes sense that the breakup would expose a layered structure, leading to that organised linear fragmentation pattern. Researchers are now engaged in a frantic race, comparing K1 spectra to databases of every other unusual comet ever recorded, searching for matches, looking for any pattern that might provide a clue. Are there other carbon-depleted comets with similar fragmentation behaviour? Do other golden-hued comets show these same motion anomalies? The sample size is tragically small, the data is frustratingly incomplete, but patterns are beginning to faintly emerge. K1 is not unique in every single respect, but the specific, potent combination of traits it exhibits remains profoundly rare. The missing carbon also raises profound questions about where and how K1 was born. If it's truly from the Oort cloud, what possible conditions out there could produce such a depletion? If it's from interstellar space, what kind of stellar environment could create this specific chemistry? And if it is related to 3I Atlas, how did two objects with unusual yet different chemistries end up arriving at our solar system's doorstep within mere months of each other? The spectroscopic mystery doesn't even end with carbon. Other elemental ratios also appear anomalous, though the data is still preliminary. Nitrogen compounds show unexpected abundances. Sulfur emissions are weaker than predicted. The overall picture is of an object whose chemistry is an ill-fitting piece in the puzzle of our solar system, whose composition suggests either unusually alien formation conditions or extensive, brutal processing after its formation. What breaks next in this story is the structure itself. How does a comet fragment in the precise, clean way that K1 did? What kind of internal architecture allows for such an organised splitting, as opposed to a chaotic, explosive disintegration? That question pulls us into the complex realm of nucleus modelling, structural mechanics, and the fundamental physics of how icy bodies fail under stress. And that is where things get truly, deeply strange. Look closely at the images from November 12th compared to those from November 13th. The fragments of K1 Atlas do not appear as a random scatter of debris. They are arranged in a loose, linear chain, separated by relatively regular intervals, each one trailing its own miniature, glowing coma. This is not what a chaotic breakup looks like. This is not the debris cloud you would expect from a comet simply exploding under thermal stress or being shredded by tidal forces. This looks organized, structured, almost deliberate. When a comet nucleus fragments, the expected outcome depends entirely on how it breaks. A sudden, explosive disruption scatters material in all directions, creating a diffuse cloud that spreads rapidly and becomes increasingly difficult to track. Individual fragments blur together, their comas overlapping, their trajectories tangling into an impossible-to-model mess. A slower, more controlled breakup might produce a few distinct fragments, but even then, the spacing would be random, determined by the specific chaotic cracks and weaknesses in the structure. K1's fragments did not scatter randomly. They aligned. The spacing between them suggested a disturbing regularity, intervals that might reflect the comet's rotation period, or perhaps its internal layering. The fragments appear to have separated along a common axis, as if the nucleus split along a pre-existing plane of weakness, shedding layers sequentially rather than disintegrating all at once. In the analysis of this pattern, two distinct camps have emerged. Camp A argues that it is still natural, still explainable within the known boundaries of comet physics. They propose that an outburst driven by a sudden volatile release, combined with rotation and thermal stress gradients, could produce sequential shedding along the equator. If the nucleus was spinning and heated asymmetrically, material could theoretically peel away in layers, with each layer separating at regular intervals determined by the rotation period. In this view, the alignment is merely coincidental, a result of our specific viewing geometry, making a three-dimensional breakup appear unnervingly linear from our perspective. Camp B finds the alignment too neat, the spacing too regular, the plume too directed. They argue the pattern strongly suggests a sophisticated internal structure, pre-existing fractures, or a layering that predates the breakup itself. Maybe the nucleus was never a single, solid body, but rather a collection of smaller pieces, weakly held together by gravity and ice. A rubble pile that finally came apart under solar heating. Or maybe the nucleus had internal planes of weakness, boundaries between layers of different composition or density, and those predetermined boundaries defined exactly where and how the object would fracture. Computer modeling efforts provide some insight. If you assume a rotating nucleus with a period of several hours, typical for comets, and you assume thermal stress creates cracks perpendicular to the heat flow, you can generate fragmentation patterns that superficially resemble what K1 showed. The spacing between fragments would depend on how fast the rotation is and how quickly the material separates. Run the numbers, plug in reasonable values, and you can get intervals similar to what the observations show. But the models also reveal severe limitations. They work best for symmetrical nuclei, for uniform composition, for predictable outgassing. K1's unusual chemistry and profound motion anomalies strongly suggest the nucleus was neither symmetrical nor uniform. The models can approximate the pattern, but they struggle to match every single detail. The plume under the leading fragment in particular doesn't fit neatly into any standard breakup scenario. Why would one fragment have such a persistent directional emission while the others appeared relatively quiet? Consider the possibility of a rubble pile nucleus. Many comets are thought to be just that, loose aggregates of smaller pieces held together by weak gravity and the frozen glue of various ices. When heated, the ice vaporizes, the cohesion vanishes, and the rubble pile comes apart. If K1 was such an object, the fragments might simply represent individual subcomponents that were once bound together. The spacing would then depend on how those components were originally arranged, and the alignment might merely reflect the structure's geometry before the breakup. Alternatively, consider a layered monolithic nucleus. If the comet formed through gradual accretion, layer upon layer of ice and dust settling onto a growing core, it might have internal boundaries where the composition or density changes abruptly. These boundaries would be natural fracture planes, weak spots where thermal stress would concentrate. A layered nucleus splitting along such boundaries could indeed produce the sequential fragmentation pattern K1 so dramatically displayed. Then there is the more exotic possibility that the nucleus possessed a structure completely unlike anything we've ever seen before. If K1 is indeed an interstellar interloper, or a fragment of a much larger alien body, its internal architecture might not resemble that of typical Oort cloud comets at all. Interstellar objects could have experienced radically different formation processes, different thermal histories, different radiation exposure. They might be more homogeneous, or more fractured, or composed of materials that behave in ways we haven't even begun to model. The technical challenge in modeling K1's breakup lies in the sheer number of unknowns. We don't know the nucleus's exact size, shape, density, composition, rotation state, or internal structure. We don't know how strong the material was, how porous, how layered. We have the fragments, their positions, their velocities, and their light curves. But we are trying to work backward from those final observations to infer properties we can never directly measure. It is like trying to reconstruct a cathedral's precise architecture from nothing but photographs of its collapse. Fragment spacing analysis tentatively suggests a rotation period of roughly 6 to 8 hours, consistent with other comets of a similar size. The intervals between the fragments imply material separating every rotation cycle, each spin shedding another layer. If true, this would support the layered shedding model. The nucleus rotated, was heated unevenly, and each time the weak boundary between layers rotated to the hottest point, it fractured and released another piece. But here is the convergence that makes scientists profoundly uncomfortable. The linear breakup pattern, combined with the fast motion anomalies, combined with the unusual chemistry, adds up to an object that doesn't fit comfortably into any single known category. Each individual trait can be explained away with some effort, but explaining them all together requires either a very specific and statistically unlikely set of coincidences, or a brave recognition that K1 might be fundamentally different from most comets we have ever studied. Could this be the visible evidence of a once larger body fragmenting in the distant past? Could K1 and 3I Atlas both be pieces of a single parent object that broke apart long before either fragment ever reached our detection range? If a large interstellar body entered the outer solar system and disintegrated due to tidal stress, internal heating, or a collision with other debris, the resulting fragments would enter the inner solar system on related but distinct orbits. They might arrive months or even years apart, each one showing signs of that primordial structural damage, each one behaving unusually compared to a pristine, stable comet. The organized breakup we witnessed might then not be the initial fragmentation of K1 itself, but rather the final, delayed disintegration of an already damaged fragment. Imagine a piece of a larger body, already fractured and cracked, held together tenuously by its remaining ice. As it approaches the Sun, that final ice sublimates, the weak cohesion fails completely, and the fragment comes apart along its pre-existing cracks. The result would look like an organized breakup, precisely because it isn't a fresh fracture, but the opening of old cosmic wounds. This hypothesis remains speculative, entirely unproven, and dependent on circumstantial evidence, but it provides a compelling framework for understanding why K1 behaves the way it does. It suggests that what we are seeing is not anomalous for a damaged interstellar fragment, but rather exactly what we should expect from such an object. The 48 hours between November 12th and 13th may have captured not just a comet breaking apart, but possibly the culmination of a process that began millions of years ago in another star system under conditions we can only guess at. And if that is true, then the next terrifying question becomes, how many more such fragments are currently inbound, silent and dark, on their way to us? The 3I Atlas looms large over this entire mystery, forcing us to ask, is K1 a twin or merely a cousin from the same cosmic stream? The story of this connection begins on July 1st, 2025, when the Atlas Survey Network detected a new object moving through the inner solar system. Initial observations immediately revealed a hyperbolic orbit, a velocity so high it could not possibly have originated from our solar system. Within weeks, astronomers had confirmed it. 3I Atlas, the third interstellar object ever discovered, the first since 2I Borisov in 2019. A genuine visitor from beyond, travelling through our celestial neighbourhood on a trajectory that would inevitably carry it back out into the galaxy, never to return. 3I Atlas exhibited peculiarities from the very beginning. Its orbit was steeply inclined to the ecliptic plane, coming in almost perpendicular to the main disk of our solar system, a path unlike any native comet or asteroid. Its velocity exceeded the Sun's escape speed by a comfortable margin. There was no ambiguity about its interstellar nature, and as the world's most powerful telescopes turned to study it, the object began to reveal a chemistry and behaviour utterly unlike any solar system comet. The James Webb Space Telescope captured detailed spectra showing an unusually high ratio of carbon dioxide to water. While most comets sublimate primarily water ice, with CO2 as a secondary component, 3I Atlas showed the exact opposite. CO2 dominated, water was secondary. This inversion strongly suggests formation in a completely different environment, possibly around a star much cooler than our Sun, where CO2 ice would be more stable and water ice far rarer. Polarimetry measurements added another layer of mystery, revealing extreme negative polarization, a property indicating surface particles with bizarre optical characteristics. The light reflected from 3I was polarized in a direction opposite to what most comets show, suggesting either an unusual dust composition or a surface texture we have never encountered before. The object also displayed a pronounced red spectral slope, meaning it reflected more red light than blue, another clear indicator of surface properties distinct from the comets we know. 3I's motion through the solar system was swift and decisive. It passed perihelion in early August 2025, coming no closer than roughly 1.5 astronomical units from the Sun, a safely distant passage compared to K1's daredevil dive. It then began its outbound journey without fanfare. By the time K1 fragmented in November, 3I was already receding, a fading speck heading back toward the interstellar darkness, unlikely to ever return. But here is where the story circles back upon itself with unnerving symmetry. K1 Atlas was itself discovered on May 24, 2025, a full 2 months before 3I's detection. At that time, K1 appeared to be nothing more than an ordinary long-period comet, inbound from the Oort cloud on a highly elliptical but still bound orbit. Its designation came from the very same survey network that would later discover its strange sibling. Both objects carry the Atlas name. Both appeared within a few months of each other. Both, we now know, exhibited deeply unusual behaviours. The hypothesis that K1 and 3I might be related emerged almost immediately after K1's fragmentation. The coincidence seemed too strong, too potent to ignore. Two objects, both discovered by Atlas, both showing chemical and motion anomalies, both arriving in the same remarkable year. Could they be fragments of a single larger parent body? Could K1 actually be another interstellar visitor, simply misclassified due to ambiguous orbital data? Orbital mechanics provides some constraints, but also deepens the mystery. 3I's trajectory is unambiguously hyperbolic. Its orbital eccentricity is well above 1, its velocity clearly interstellar. K1's orbit, according to all published data, is elliptical, with a period of roughly 30,000 years, typical for long-period comets from the Oort cloud. On the surface, the two orbits don't obviously intersect or share common characteristics. If both objects did come from the same parent body, that primordial fragmentation would have had to occur far enough out that gravitational perturbations and differing velocities could put the fragments on significantly different paths. Some researchers propose a scenario where a large interstellar body entered the outer solar system several years ago, perhaps even decades ago, and broke apart due to tidal stress from the Sun's gravity or a close encounter with Jupiter. The fragments would then separate, each following its own unique trajectory, some remaining on bound orbits around the Sun, others retaining enough velocity to escape back into interstellar space. In this model, 3I might be a fragment that kept its interstellar speed, while K1 might be a piece that lost just enough velocity to be captured by the Sun's gravity, falling into a bound orbit and masquerading as an Oort cloud comet. This scenario requires very specific conditions. The parent body would need to be large enough that fragments could have significantly different velocities after the breakup. The fragmentation would need to occur in a region of space where solar and planetary gravity could capture some pieces while allowing others to escape, and the timing would need to work out with almost poetic precision so that the fragments arrive in the inner solar system within months of each other, despite having separated years or even decades earlier. Observational support for this hypothesis is limited but undeniably intriguing. Both objects show anomalous chemistry, though in different ways. Both exhibit unusual motion, though the specific details differ. Both were discovered by the same survey, though that is largely because ATLAS is one of the most sensitive and wide-ranging sky surveys currently in operation. The naming convention itself is, of course, purely coincidental. ATLAS names objects based on discovery date and survey location, not on any physical relationship. Scientific skepticism regarding this connection is strong, and rightly so. Coincidences happen all the time in astronomy. With thousands of objects being discovered each year, some will inevitably share superficial similarities without being physically related. The burden of proof lies squarely with anyone claiming a connection, and so far, the evidence remains entirely circumstantial. The orbital data for K1 continues to indicate an Oort cloud origin, not an interstellar one. Its chemistry, while unusual, is not impossible for a solar system comet. Its fragmentation, while organized, doesn't definitively prove an exotic origin. And yet, the relentless accumulation of anomalies keeps the hypothesis disquietly alive. If K1 were a typical Oort cloud comet, why the profound carbon depletion? If its motion is explained by normal outgassing, why is it so fast and so directional? If its breakup is natural and unremarkable, why the linear pattern and regular spacing? Each of these questions has potential answers within the bounds of conventional comet science, but those answers require a very specific set of conditions, fortunate alignments, and unusual, though not impossible, circumstances. Multiply enough of those unlikely requirements together, and you inevitably start wondering if a simpler, more unified explanation exists. This line of thinking introduces the concept of interstellar debris streams. What if these objects don't arrive as solitary wanderers, but as clusters of fragments, as members of a larger family? Then our solar system might be peppered with interstellar material far more often than we have ever realized. We have only confirmed 3 interstellar objects in the entire history of astronomy: 1I Oumuamua, 2I Borisov, and 3I Atlas. But how many more have we missed? How many objects entered the solar system before we had the technology to detect them? How many are too faint, too small, or too distant for our current surveys to catch? If K1 is indeed related to 3I, then we are witnessing not isolated, rare visitors, but members of a stream, fragments of a single disrupted body making their way through our neighborhood. This single idea shifts the entire narrative. It transforms the phenomenon from a series of rare, singular events into an ongoing, natural process. It suggests that interstellar material might be far more common than we thought, that our solar system's boundary is more porous, more frequently crossed by visitors from other star systems. Imagine a large interstellar body, perhaps several kilometers across, approaching the solar system's gravitational well. As it falls inward, solar and planetary tides stress its structure to the limit. If the body is already fractured from previous cosmic encounters or from its own internal processes, it might come completely apart, releasing fragments that fan outward like shrapnel from an explosion. Some pieces gain velocity from the encounter and escape. Others lose energy and settle into long, bound orbits. The result is a vast debris field, spread across years of time and across immense distances, with individual fragments arriving unpredictably over time. This scenario is not proven, not confirmed, but it provides a powerful and elegant framework for understanding what might otherwise seem like disconnected, bizarre events. K1 and 3I might be siblings in a cosmic sense, born from the same parent, scattered by the violence of their breakup, arriving separately in our skies, but forever connected by their shared origin. The question lingers in the data, in the silent, digital records of telescopes around the world, as both objects continue their separate journeys. 3I is already beyond the orbit of Mars, fading from view, racing back toward the eternal darkness between the stars. K1's fragments continue their own spread outward, tracked by those same telescopes, analysed by spectrographs, modelled by supercomputers desperately trying to reconstruct what happened and why. Whether they are truly related or merely coincidentally similar remains unresolved, but the possibility hangs in the air, in the timing, in the shared, profound strangeness of their behaviours. What we have established in these first 5 parts is a solid foundation of anomalies, a fragmentation that looks orchestrated, motion that defies simple explanation, chemistry that doesn't match our expectations, and a timing that coincides almost perfectly with another bizarre object from interstellar space. None of this, on its own, proves anything definitively exotic, but all of it, together, is a powerful, undeniable invitation to a deeper investigation. The obvious questions have now been asked. It is time to dig into the less obvious ones, the angles that don't make headlines, but which might, in the end, hold the real answers. We are about to enter territory where archived data meets bold speculation, where established models clash with uncomfortable new data, and where the fringe theories begin to look, for the first time, a little less absurd. The story of K1 Atlas does not begin on the night it fractured. The first faint whispers of its arrival were hidden in the archives, buried in the noise of countless survey logs. Professional telescopes scan the sky every single night, their electronic eyes capturing the positions, magnitudes, and motions of millions of objects. Most of these detections are routine, known asteroids, catalogued stars, distant galaxies. But sometimes, the automated systems flag something transient, a faint signal that appears in 1 or 2 images and then vanishes before follow-up observations can confirm its reality. These are the ghosts of the database. Faint signals that might be real objects, or might be cosmic ray hits, satellite glints, or simple processing artifacts. In the years between 2022 and 2024, several such ghosts appeared in the Atlas survey logs. They were faint, transient detections on inbound trajectories, moving through regions of the sky that would later, with the benefit of hindsight, align suggestively with K1's projected path. At the time, these signals were too weak for any meaningful follow-up, too uncertain for classification. They were entered into the database and marked as unconfirmed, as possible false positives, objects that might not exist at all. It was only after K1's dramatic fragmentation that researchers, combing through this archival data with a new, specific purpose, found these forgotten entries. The positions weren't perfect matches, but the trajectories were eerily similar. If you extrapolate backward from K1's well-defined orbit, carefully accounting for gravitational perturbations and orbital uncertainties, its path passes tantalizingly close to the locations of some of these ghost detections. Could they have been early, missed glimpses of K1 itself, before it brightened enough for official confirmation? Or, more intriguingly, could they have been other, smaller fragments of the same debris stream, pieces that passed through our neighbourhood completely unnoticed? The evidence is not limited to optical surveys. NEOWISE, the infrared space telescope that specialises in detecting asteroids and comets, also recorded its own anomalies during this period. In April 2024, a faint thermal signature appeared in data from a region of sky with unusual ecliptic coordinates. The detection was weak, barely above the instrument's noise floor, and it disappeared before additional images could confirm it. The automated cataloguing system flagged it as a probable instrumental artifact. No follow-up was ever conducted. This detection sat dormant in the archives for over a year before anyone thought to look at it again in the new context of the K1 mystery. The thermal signature's position and motion vector, when painstakingly reconstructed from the limited data, suggest an object on a steeply inclined orbit moving inward toward the Sun. The timing would place its passage roughly a year ahead of K1's own discovery. If it was real, it might represent another, earlier fragment of whatever stream K1 belongs to, a piece that passed through the inner solar system ahead of the main body. These pre-arrival detections are maddeningly ambiguous. Survey telescopes generate false positives constantly. Cosmic rays strike the CCDs and create bright spots that mimic stars or asteroids. Satellites cross the field of view and leave streaks of light. Processing algorithms sometimes misidentify random noise patterns as real signals. Statistically, any individual ghost detection is far more likely to be spurious than real. But when multiple ghosts appear along similar trajectories within a related time period, the probability of mere coincidence begins to decrease significantly. Think of it like a meteor shower. When Earth passes through the debris stream left by a comet, we see hundreds of meteors streaking across the sky over several nights, all appearing to originate from the same general direction. We only see the visible meteors, the ones that enter our atmosphere and burn brightly enough for our eyes or cameras to detect. But the stream itself contains thousands of other particles, too small or too sparse to be seen from the ground. K1 might be the bright, obvious member of a similar interstellar stream, with other, fainter fragments passing through undetected, their presence hinted at only by these faint, ghostly signals in the survey data. The monumental challenge in confirming these ghosts lies in the inherent nature of survey work itself. Telescopes scan the sky on fixed schedules, imaging each region of space every few nights. If an object is moving fast enough, or is simply too faint, it might appear in only one or two images before it moves out of the field of view. Without multiple, linked detections to confirm its motion and refine its orbit, the object can never be verified. It remains a ghost, a possibility, a tantalizing maybe, forever trapped in the archives. Some orbital simulations show that if a large interstellar body did disintegrate far out in the solar system, perhaps at distances of 50 to 100 AU, the resulting fragments would slowly spread out over time. Slightly different velocities and trajectories would cause the fragments to arrive in the warmth and light of the inner solar system, months or even years apart. An observer on Earth would see them as separate, unconnected events, unless someone thought to compare their orbits with a deep and open mind, looking for a common origin. The orbital dynamics of such a scenario are fiendishly complex. Gravitational perturbations from Jupiter, Saturn, and the Sun itself would alter each fragment's trajectory differently, depending on exactly when and where the fragment passed near a planet. Two fragments starting on nearly identical paths could end up on wildly different orbits after just a few planetary encounters. This makes it incredibly difficult to trace individual fragments back to a common origin, even if that origin truly existed. Survey bias also plays a major, often unappreciated role. Telescopes are not equally sensitive in all directions or at all times. Faint objects near the Sun's blinding glare are much harder to detect than those in dark, opposition skies. Objects moving rapidly across the field of view might be missed by automated tracking algorithms that are tuned for slower-moving main belt asteroids. An object on a steeply inclined orbit might pass through regions of the sky that are scanned less frequently. All of these factors mean that some real objects inevitably slip through the net, going completely undetected, while others are caught by chance. What if K1 is not the first fragment of its stream to enter our detection range, but merely the first one that was bright enough and slow enough to be confirmed? What if the survey logs are filled with the faint, spectral evidence of earlier arrivals? Ghosts that mark the silent passage of smaller or faster-moving pieces. This single possibility transforms the entire narrative from a story about a single, bizarre object to a story about a stream of objects, from an isolated, anomalous event to an ongoing, natural process. The historical survey data will never provide certainty. The ghosts are too faint, the detections too uncertain. But they add a crucial layer of context. They suggest that whatever K1 is, it might not be alone. They hint at a bigger picture, a scenario where small interstellar bodies, or their fragments, arrive more often than our handful of confirmed detections would suggest, most of them slipping through our observational net, except on those rare occasions when one is large enough, or bright enough, or slow enough to be caught. If this hypothesis has any merit at all, then we should logically expect more such detections in the coming years. As sky surveys improve, as telescopes become more sensitive, as automated systems get better at recognizing true transients, we will inevitably catch more of these ghosts and turn them into confirmed, catalogued objects. The official rate of interstellar object detections might increase dramatically, not because more are suddenly arriving, but simply because we are finally getting better at seeing what has been there all along. The pre-arrival mystery doesn't prove anything concrete about K1's origin, but it does suggest we should be cautious in assuming we know how often interstellar material visits our solar system. Our current estimates are based entirely on the few, bold visitors we have confidently confirmed. But if the archives are secretly filled with unconfirmed ghosts, if faint fragments pass through our celestial neighbourhood unnoticed all the time, then our estimates might be far too conservative. Interstellar visitors might be a much more common feature of our cosmic environment than we have ever dared to believe. Now, having established that K1 might not be arriving alone, that it could be part of a larger, hidden pattern scattered across archival data, we must move to the most fundamental question of all. What is K1, actually? What is its internal structure? What is it made of? What kind of object fails in the precise, strange way that K1 did? That is where the scientific models truly clash, and the uncertainty becomes not just a detail, but the entire story. Every comet that fragments teaches us something new about the internal structure of these ancient icy bodies, about how dust and ice hold together to form objects that can survive for billions of years in the deep freeze of space, only to crumble in a matter of hours when the sun's heat finally finds a critical weakness. The fragmentation of K1 Atlas invites three competing explanations, each based on radically different assumptions about what the nucleus was made of and how it was originally assembled. The first and most conventional model treats K1 as a weak rubble pile. This is the default assumption for the majority of comets. In this view, the nucleus was never a single, solid object, but rather a loose, fragile aggregate of smaller chunks, ranging in size from pebbles to boulders, all held together by nothing more than their own weak mutual gravity and the frozen ices acting as a temporary cement. This structure is common and neatly explains why comets tend to fragment so easily. When solar heat sublimates the ice, the cohesion simply vanishes, and the rubble pile comes apart like a sandcastle undermined by an incoming tide. According to this model, rubble pile nuclei fragment gradually and somewhat randomly. As the ice melts, pieces shake loose and drift away. The separation speeds are typically low, mere meters per second or less, determined by the weak gravity binding them and the gentle nudge of escaping gas. You would not expect to see organized patterns or clean linear alignments unless the object's rotation happens to fling material out preferentially along its equator. K1's behavior fits this model in some superficial respects. The fragmentation did occur after perihelion, when solar heating was at its most intense. The measured separation speeds were, at first glance, consistent with weak gravity and outgassing, and the fact that it broke into multiple fragments suggests a body that was never truly cohesive in the first place. But the rubble pile model struggles profoundly when confronted with K1's other attributes. If the nucleus was composed of typical Oort cloud material, why the severe carbon depletion? If the structure was a loose aggregate, why the unnervingly organized linear pattern of fragments? If the outgassing was normal, why the rapid, sustained divergence of the fragments? You can force the model to work if you add a host of special conditions: unusual composition for the rubble, a very specific rotation state, intensely asymmetric heating. But each new addition reduces the model's elegance and simplicity, making it seem more like an ad hoc excuse than a genuine explanation. The second model proposes a different structure, a monolithic but brittle body. This is less common for comets, but is observed in some asteroids. Here, the nucleus is envisioned as a single, coherent piece of material, perhaps formed through gentle, low-speed collisions that allowed tiny particles to stick together into a solid mass. This structure is inherently stronger than a rubble pile, but it is still prone to catastrophic fracture under sufficient stress. Thermal gradients can create immense internal tension as the surface heats and expands while the cold interior remains unchanged. Eventually, the stress exceeds the material's tensile strength and the body cracks. A monolithic, brittle nucleus would fracture along its inherent planes of weakness, producing clean breaks and well-defined fragments. The fragmentation could be sudden and organized, with pieces separating along pre-existing structural boundaries rather than crumbling apart chaotically. This model does a much better job of explaining K1's linear pattern. If the nucleus had internal layers or planes of weakness perpendicular to its rotation axis, it might very well split along those planes, releasing fragments in a neat, orderly line. The persistent, directed plume also fits more comfortably into this model. A sudden crack in a monolithic body could open a pathway, releasing the pressure from sublimating ices that were trapped beneath the surface, producing a jet that persists as long as the exposed ice continues to vaporize. The fragment with the bright plume might have simply cracked in a way that exposed a particularly volatile rich layer, driving the sustained emission. Yet the monolithic model has its own serious problems. Monolithic comets are thought to be quite rare, and those that do exist usually show clear evidence of the structural strength that K1 seem to lack. The rapid fragmentation and the large number of pieces suggest a weak, not a strong material, and once again, the chemistry remains a puzzle. Why would an Oort cloud comet, formed from the same solar nebula as everything else, show such a profound depletion of carbon? The third model introduces the most radical variable, exotic composition. This model proposes that K1's nucleus was made of materials we don't typically encounter in solar system comets. This could mean unusual ice mixtures, high ratios of carbon dioxide or carbon monoxide to water, or even materials that formed in a completely different stellar environment with fundamentally different chemical abundances. The structure might still be a rubble pile or monolithic, but the very substances making up that structure are different from the standard cometary recipe. An exotic composition model naturally and elegantly explains the carbon depletion and the unusual chemistry. If K1 formed around a different star, or in a molecular cloud with different abundances, or was heavily processed by radiation during its long interstellar journey, its chemistry would inevitably differ from Oort cloud norms. Carbon dioxide ice, for instance, sublimes at a higher temperature than water ice, and could potentially drive more violent outgassing, which would in turn explain the motion anomalies. Extensive radiation processing could also weaken the structure over millions of years, making fragmentation far more likely. Here, 3I Atlas provides a compelling comparison. That object's high carbon dioxide to water ratio, as definitively measured by the James Webb Space Telescope, indicates formation in conditions starkly different from our solar system's comet-forming regions. The chemistry suggests an environment where CO2 was more abundant or where water ice was depleted, possibly around a cooler star where the respective snow lines were located much closer in. If K1 shares a similar origin, its own chemistry should show similar, if not identical, departures from solar system norms. The exotic composition model also handles the structural mystery more gracefully. If the nucleus contains CO2-rich ices, those ices would sublimate rapidly when heated, creating intense internal gas pressure that could fracture even a relatively strong structure. This rapid gas release would drive the fast outgassing, producing the observed motion anomalies and those bright, persistent plumes. The fragmentation pattern would then simply reflect how the body breaks under this internal pressure, likely along planes where different ice compositions meet, creating natural fault lines. However, proposing an exotic composition requires extraordinary evidence. Claiming that a comet formed in another star system or was radically altered in interstellar space is a huge leap from simply observing unusual chemistry and an odd breakup. The burden of proof is appropriately high, and rightly so. Many scientists remain deeply skeptical, arguing forcefully that natural variation within our own solar system's vast comet population can account for K1's traits without needing to invoke the spectre of interstellar origins. The internal controversy among astronomers reflects these competing models perfectly. One camp insists that K1 is simply a comet, unusual in some respects, but still well within the natural, if poorly sampled, range of variation for such objects. The other camp argues that the accumulation of so many significant anomalies pushes the object far outside that range, strongly suggesting something more exotic is at play. This debate is healthy. It drives more observations, more sophisticated modelling, and more rigorous attempts to test each hypothesis against the hard, unforgiving data. Fragmentation modelling has advanced significantly in recent years. Researchers can now simulate comet nuclei with different compositions, structures, and rotation states, then apply virtual solar heating and watch how these digital objects break apart. These simulations are crucial for constraining what K1 might have been like before it fractured. Preliminary results suggest a nucleus perhaps 2 to 3 kilometers across, rotating every 6 to 8 hours, with internal layers separated by boundaries where the composition changed abruptly. The fragment spacing provides critical clues. If pieces separated every rotation cycle, and if we know the rotation period and the separation speed, we can estimate the thickness of the layers that were shed. The numbers tentatively suggest layers tens to hundreds of meters thick, consistent with either accretion boundaries in a large rubble pile or genuine compositional layering in a more monolithic body. But once again, the uncertainties are vast, and the data is still insufficient to strongly favour one model over the others. What if the true structure was neither a pure rubble pile nor a monolithic solid, but something in between? A hybrid? What if K1 was a rubble pile where the individual chunks were themselves coherent, mini-monoliths, creating a hierarchical structure? This would be like a pile of bricks, each brick solid, but the pile itself only loosely bound. Such a structure might fragment in distinct stages, first separating into its constituent boulders, and then those boulders potentially breaking apart further if they contained their own internal weaknesses. The debate over K1's structure is not merely an academic exercise. Understanding how these objects are built tells us about their origins, about how small bodies form and evolve across the galaxy, and about what happens to material ejected from one star system when it finally enters the gravitational influence of another. If K1 is an exotic visitor, it provides us with a priceless, direct glimpse into planetary formation processes around other stars. If it is a solar system native, it challenges our most basic assumptions about comet composition and structure at a fundamental level. Each model makes predictions that future observations can test. If K1 is a weak rubble pile, its fragments should continue to separate slowly, driven by residual rotation and gentle outgassing. If it is a fractured monolithic body, the fragments should be relatively stable, their structures coherent. If it is exotically composed, spectroscopy of the individual fragments might reveal additional chemical anomalies, differences between the fragments that reflect the internal layering we've postulated. The clash of models is far from resolved, and perhaps it won't be until we can one day send a spacecraft to such an object and examine it directly. But the debate itself sharpens our understanding, forces us to articulate our assumptions clearly, and reveals with painful clarity where our knowledge is solid and where it is merely educated guesswork. The structure of K1 remains uncertain, but that uncertainty is now explicit, quantified, and mapped out in competing, testable hypotheses. From the question of structure, we must now move to the question of energy. What is driving the motion and those bizarre plumes? Because if K1's fragments are accelerating faster than normal outgassing should allow, we need to account for where that extra energy is coming from and how it is being released into the cold vacuum of space. The virtual telescope images, a bright, narrow plume extends outward into the darkness. a beacon of activity that persisted across multiple nights of observation, lasting for more than 36 hours without significant fading. This was not a brief, explosive outburst. This was a sustained emission, a continuous, focused release of gas and dust from a fragment that, by all rights, should have been quieting down as it moved farther from the sun's intense heat. Normal comet jets form when sunlight heats patches of exposed ice on the nuclear surface. The ice sublimates, turning directly from a solid into a gas, and rushes outward into space at speeds of a few hundred meters per second. Dust particles, entrained in the rushing gas, create a visible plume. Such a jet typically persists only as long as the ice patch remains exposed and in sunlight, but it usually weakens over a matter of hours as the sublimating ice recedes beneath insulating dust layers, or as the nucleus's rotation carries the active region into cold shadow. K1's plume did not behave like this. Its emission persisted far beyond what simple surface heating should be able to sustain. Its structure was narrower, more columnated than typical diffuse dust-gas mixtures. Its unwavering brightness suggested a high mass loss rate, grams to kilograms of material being ejected every second, an output substantial enough to produce a measurable thrust on the fragment itself. We can compute the numbers roughly. If the plume is ejecting material at 500 meters per second, typical for sublimating water ice, and the mass loss rate is a mere 1 kilogram per second, the resulting thrust is 500 newtons. For a fragment perhaps 100 meters across, with a mass of several million kilograms, this tiny thrust produces an acceleration of roughly 0.005 meters per second squared. It seems minuscule by everyday standards, but in the frictionless environment of space, integrated over hours and then days, it adds up to velocity changes of meters per second, precisely enough to explain the observed motion anomalies that so puzzled orbital dynamicists. The energy required to sustain this emission has to come from somewhere. Solar heating is the obvious and primary source, but the fragment was moving away from the sun, cooling down, receiving less and less energy with each passing hour. And yet, the plume persisted, bright and unwavering. This means the fragment must have had internal heat stored from its recent perihelion passage, slowly releasing as sublimation fronts worked their way inward through the icy matrix, or, more provocatively, that something else was providing an additional source of energy. Internal heat storage is a plausible mechanism. Ice is a poor thermal conductor, so heat absorbed at the surface during the close solar approach can take days to conduct inward toward the core. As it does, it reaches deeper, previously untouched ice layers and drives sublimation beneath the surface. The resulting gas builds up pressure, finds a weak point or a vent, and escapes, creating the observed plume. This delayed action mechanism is well understood and has been observed in other comets. But K1's plume seems stronger and more persistent than this mechanism alone should produce. The fragment was relatively small, its cooling should have been relatively fast, and the internal heat should have dissipated within a matter of hours, not days. Yet the observations clearly showed the emission continuing with undiminished vigour beyond what the simple models predicted. This forces us to ask, could the internal structure itself be playing a role? If the fragment contains voids or sealed fractures, sublimating gas might build up pressure in these hidden cavities, only to be released suddenly when the pressure finally breaches a weak point. This would create jets that are far more energetic than those produced by simple surface sublimation. The fragment, in this view, could be acting like a pressure vessel, storing thermal energy in the form of high-pressure gas, and then releasing it in a focused, directed flow. Once again, 3i Atlas provides a compelling parallel. Images and polarimetry of that object showed columnated jets extending over 1 million kilometers, far longer and more structured than typical comet jets. The persistence and narrow structure of those emissions suggested a sustained, directed release mechanism rather than simple, diffuse outgassing. If K1 is related to 3i, it is not unreasonable to suspect that similar, unknown emission mechanisms might be at work in both objects. The thrust from this persistent plume has a direct and measurable effect on the fragment's trajectory. If the emission is asymmetric, pointing more in one direction than any other, it acts like a tiny natural rocket engine, continuously changing the fragment's velocity vector. Over time, this changes the orbit, producing the very non-gravitational accelerations that the tracking data so clearly revealed. The fragment isn't following a purely gravitational path because it is not just a passive rock falling through space. It is actively, though unintentionally, propelling itself, pushed by its own violent emissions. This raises a speculative but deeply intriguing possibility. If the jet is not purely the result of natural surface-level outgassing, but indicates a deeper internal pressure release or structural venting, could it be evidence of an internal architecture we don't normally expect? Could cavities, channels, or chambers within the fragment be controlling how the gas escapes? Could the object's very structure be acting to focus and direct the flow? The idea might sound far-fetched, until you remember that some researchers have proposed exactly this to explain the features of 3I Atlas. Its columnated jets, unusual polarization, and persistent emissions all hint at a level of structure beyond what a simple, homogeneous rubble pile should possess. If 3I contained internal voids or a layered architecture, those features would profoundly affect how gas escapes and could create the strange emission patterns we observed. K1's fragment, with its bright, unwavering plume, might be giving us a close-up, detailed view of these same processes in action. The plume's persistence and narrowness could be reflecting not just chemistry, but geometry, the specific shape of the vent, the detailed structure of the interior, the precise pathways that gas must travel through fractures and cavities before finally erupting into space. Energy budget calculations help to constrain the possibilities. The observed brightness of the plume tells us how much dust is present. The spectrum reveals the gas composition. Combined, these measurements constrain the total mass loss rate. The velocity of the plume, which can be measured from how fast it expands, tells us about the gas temperature and pressure at the point of venting. All of these numbers feed into complex models that try to replicate what we see. Preliminary models suggest mass loss rates that are higher than expected for passive sublimation alone. Something is driving a more vigorous emission. It could be higher internal temperatures than surface sunlight should provide, or higher gas production rates than typical ice chemistry allows, or structural features that focus the emission into a narrow, efficient jet. The fragment might be unusually volatile rich, with high concentrations of CO2 or CO that sublimate much more readily than water ice. Or it might possess structural features that naturally channel gas into a narrow jet, rather than allowing it to diffuse away broadly across the surface. The comparison to a thruster is not meant to imply anything artificial, but rather to highlight the simple physical fact that the emission produces a measurable and sustained thrust. The fragment is not passive. It is dynamically active, changing its own trajectory through its emissions. While this is normal comet behavior in principle, the magnitude and persistence of the effect in K1 are at the extreme upper end of anything we have ever observed. To visualize this, imagine the fragment as a spinning, potato-shaped rock, several hundred meters long, tumbling slowly. On one side, a fissure or vent acts as a nozzle, releasing a steady stream of gas and dust, a plume that extends for thousands of kilometers into the surrounding blackness. The gas molecules, moving at hundreds of meters per second, carry momentum away from the fragment, and by Newton's third law, the fragment recoils, accelerating in the opposite direction. The emission isn't perfectly constant. It likely varies with the rotation, brightening when the vent points toward Earth, dimming when it rotates away. But over days, this continuous process changes the fragment's orbit in a measurable way. The acceleration is tiny, almost negligible, but space is a vacuum without friction, and velocity changes accumulate relentlessly. By the time weeks have passed, the fragment is kilometers away from where purely gravitational predictions would have placed it. This is exactly what the tracking data shows: offsets that grow over time, accelerations that are perfectly consistent with a directed, persistent source of thrust. The energy budget imbalance doesn't prove anything exotic on its own, but it does powerfully constrain our explanations. Whatever K1 is, it contains enough volatile material to sustain significant outgassing for an extended period. It has an internal structure that permits this directed emission, and it responds to solar heating in a way that produces a measurable, trajectory-altering thrust. These are not small details. They are critical constraints that dramatically narrow the range of possible compositions and structures for this object. The thruster analogy also seamlessly sets up the next, overarching question. If K1 is part of a larger pattern, if it isn't arriving alone, but as part of a stream of related fragments, then maybe what we are seeing is not a single, odd object breaking up, but a preview of things to come. Maybe interstellar fragments don't typically arrive as pristine, intact bodies, but as pre-damaged debris, as pieces of a whole, spread across time and space. Each one potentially active, each one emitting, each one slightly altering its own path through its own internal processes. This line of thinking leads us directly to the most sweeping hypothesis of all, one that could rewrite our understanding of our place in the galactic community. The traditional textbook picture of interstellar objects is clean, simple, and lonely. A single body, ejected from the chaotic planetary formation process around another star, wanders the immense, empty stretches of the galaxy for millions of years, eventually passing through our solar system as a brief, solitary visitor, never to return. One-eye Oumuamua fit this picture. Two-eye Borisov fit this picture. Three-eye Atlas on the surface also fit this picture. Solitary travelers, unique events, rare, almost miraculous encounters. But what if this comforting picture is wrong? What if interstellar objects do not usually arrive as intact, pristine bodies, but as streams of fragments, as debris from larger bodies that broke apart long before they ever entered our detection range? What if, for every confirmed interstellar object we see, dozens or even hundreds of smaller fragments pass through our solar system completely unnoticed? The interstellar drift hypothesis proposes exactly this. It suggests that when large objects are ejected from their parent star systems, during planetary migrations, stellar encounters, or other violent events, they do not always survive the ejection process intact. Gravitational tides from the parent star, collisions with other debris, internal stresses from rapid rotation, and the relentless pressure of stellar radiation can all fragment a body while it is still relatively near its birthplace. The resulting fragments then disperse, each carrying a slightly different velocity, and are then spread across time and space by the complex dynamics of the galaxy itself. Sophisticated simulations of galactic shear show that debris from a single disrupted body can spread out into elongated streams hundreds, if not thousands, of astronomical units long. The fragments start on similar paths, but minute velocity differences compound over millions of years of travel. By the time this stream of debris encounters another star system, like our own, the fragments can be separated by light years of space, arriving at their destination not in a group, but strung out across years or even decades. The evidence for such streams is currently indirect, but the concept is sound. We see the same principle at work in our own solar system. Meteor showers on Earth are nothing more than debris streams from comets like Swift-Tuttle or Halley. The fragments are spread along the comet's orbit, and we encounter them predictably each year as Earth's orbit carries us through the stream. The same principle could easily operate on an interstellar scale. A single disrupted interstellar body could see dozens of stars, systems with its fragments over immense spans of time, with each system seeing pieces arrive sporadically rather than all at once. K1 and 3i Atlas fit this pattern disturbingly well. Both were discovered within months of each other. Both showed bizarre, non-standard behaviour. Both exhibited chemistry and motion anomalies that strongly suggest origins far outside our local comet population. Could there be two fragments of a single larger parent body? Pieces that separated from each other eons ago and are now by chance arriving in our inner solar system along related, though not identical, trajectories. The orbital data presents the biggest challenge to this idea. 3i's orbit is unambiguously K1's orbit, as currently calculated and catalogued, is elliptical with an eccentricity less than 1, indicating a bound orbit from the Oort cloud. On paper, these two orbits do not obviously connect. If both fragments came from the same parent, that parent's disruption would have had to produce fragments with wildly different velocities and trajectories. One compelling possibility is that the disruption occurred within our solar system. Imagine a large interstellar body entering from the galactic north, passing through the outer solar system perhaps decades ago. As it travels inward, gravitational perturbations from a giant planet like Jupiter or Saturn stress its structure to the breaking point. The body fragments. Some pieces gain velocity from the gravitational slingshot encounter and escape back into interstellar space. These become objects like 3I Atlas. Other pieces lose velocity during the encounter and fall into bound orbits around the Sun. These become objects like K1, initially misidentified as Oort cloud comets because their orbits are now bound to our star. This scenario requires very specific dynamical conditions, but it is not impossible. Gravitational slingshots are a proven and powerful phenomenon, capable of dramatically changing a body's velocity. A well-timed encounter with Jupiter could slow an incoming interstellar object enough to capture it into a bound orbit, or speed up a bound object enough to eject it. If fragmentation occurred during such a close encounter, different fragments could easily end up on radically different paths, some ejected, some captured. Another possibility is that K1's orbital classification is itself ambiguous. With a limited observation arc and the inherent uncertainties in measuring the orbits of such distant, faint objects, the distinction between a very long-period elliptical orbit and a barely hyperbolic orbit can be subtle. If K1's eccentricity is actually slightly above 1, just barely interstellar, it might have been misclassified due to these initial uncertainties. More observations and a better orbital determination over time could, in theory, revise its classification. The timing, however, strongly supports the stream hypothesis. Both objects appeared in the same year, 2025, just months apart. Both were discovered by the same survey network, suggesting they passed through similar regions of the sky at similar times. Coincidence is always a possibility, but the probability of such a coincidence decreases significantly when you add in the other profound behavioral similarities: unusual chemistry, unexplained motion anomalies, and dramatic fragmentation events. The concept of intergenerational visitors adds another fascinating layer to this idea. If our solar system is currently passing through, or is embedded within, a vast interstellar debris stream, we might see fragments arriving not just over a few years, but over centuries. We might witness periodic increases in interstellar object detections, clusters of visitors appearing when Earth's orbit carries us through a denser knot of the stream. The 2025 cluster, 3I, and potentially K1, might be the first such cluster we have had the technological capability to detect and recognize for what it is. Survey programs are now actively searching for these patterns in the arrival of interstellar objects. Are the detections truly random, or do they show signs of clustering in time? Do objects arriving within short time periods share common orbital characteristics, like similar inclinations or directions of approach? The dataset is still tragically small, only 3 confirmed interstellar objects. But as more detections inevitably occur in the coming years, these patterns may finally emerge from the noise. The philosophical implication of this is profound. If interstellar visitors arrive as streams rather than as isolated individuals, our galactic neighborhood is far more populated and dynamic than we ever imagined. The space between stars is not an empty void. It is filled with debris fields, with fragments spread across vast volumes, the remnants of countless planetary systems and stellar encounters scattered throughout the galaxy. Our solar system, as it orbits the galactic center, drifts through this material constantly, encountering these fragments on a regular basis, with most of them being too small or too faint for our current technology to detect. K1 might be the first clear, visible evidence of this ongoing natural process. It is not an anomaly, it is a sample. It is a piece of the interstellar background that happened to be large enough and passed close enough to the Sun to brighten and become visible to us. If we had instruments sensitive enough to see all the fragments passing through our solar system at any given moment, we might find dozens, even hundreds, a constant, low-level rain of material from other stars, a gentle cosmic drizzle that has been falling since the solar system began. This realization reframes the entire question. Instead of asking, why is K1 so weird? We should be asking, why haven't we seen more objects like K1? Instead of treating interstellar visitors as rare, singular events, should perhaps treat them as common, but mostly undetectable phenomena. The shift in perspective is subtle, but its implications are profound. The counter-arguments to this hypothesis remain strong. The orbital data for K1 still points toward an Oort cloud origin. The spectroscopic data, while unusual, do not definitively prove an interstellar origin. The fragmentation and motion anomalies, while deeply intriguing, can still be explained within the bounds of solar system comet physics, if one is willing to accept a chain of unlikely circumstances. The stream hypothesis itself requires multiple uncertain assumptions to work. And yet, the hypothesis persists because it offers a powerful, unifying explanation. It connects dots that otherwise seem random and unrelated. It provides an elegant framework for understanding not just K1, but the broader, emerging population of small bodies entering our inner solar system. And most importantly, it makes testable predictions. If the interstellar drift hypothesis is correct, we should see more objects with similar properties appearing in the coming years, possibly clustering in time, and possibly showing shared orbital characteristics that betray their common origin. The interstellar drift hypothesis transforms K1 from an isolated oddity into a potential harbinger. It suggests that what we are witnessing is not a unique event, but the first clear detection of a phenomenon that has been happening all along, invisible to us until our technology finally became sensitive enough to reveal it. And if that is true, the implications extend far beyond the story of one fragmented comet. From the idea of natural streams of fragments, we now take a final, speculative step into territory that some researchers have begun to explore, a territory where the data forces us to ask whether some of these objects might not be natural at all. Are now entering the most speculative territory of this investigation. These are ideas that the vast majority of astronomers treat with deep skepticism, but which, fueled by the accumulation of anomalies, refuse to disappear entirely from the conversation. These are not verified facts. They are not consensus positions. They are questions raised at the farthest edges of interpretation, and they deserve mention not because they are likely to be correct, but because exploring even the most unlikely possibilities can sometimes reveal truths we would otherwise never consider. The core claim here is simple, but audacious. What if some of these interstellar objects are not natural fragments at all, but artifacts, probes sent from other civilizations, constructs rather than simple rocks and ice? What if the odd behaviors we observe, the columnated jets, the unusual chemistry, the organized fragmentation, are not mere anomalies of natural processes, but designed features of engineered systems? Avi Loeb, the Harvard astronomer who famously suggested that Oumuamua might be an artificial light, Sale, has raised similar questions about 3I Atlas. He points to its columnated jets, its unusual polarization, and certain spectral hints of elevated nickel content. Nickel in asteroids is common, but a concentrated, refined presence might, in his view, indicate processed materials, manufactured metals, structures that were designed and built, rather than haphazardly accreted from a protoplanetary disk. Loeb proposes that 3I could be a fragment of alien technology, a probe or a beacon that either malfunctioned long ago or was intentionally sent on a course through our star system. The evidence for this is thin, hotly contested, and disputed by nearly the entire astronomical community. Most scientists argue, convincingly, that every one of these features has a natural explanation. The jets from asymmetric outgassing, the polarization from unusual dust properties, the nickel from metal-rich rock that formed naturally. Extraordinary claims require extraordinary evidence, and as of now, that level of evidence is completely lacking. But then K1 appeared, exhibiting its own, distinct set of oddities. The organized fragmentation pattern, the linear alignment of the fragments, the persistent, directed plume that acted like a thruster. Taken individually, each feature can be explained by natural, if unusual, processes. Taken together, and especially in connection with the strangeness of 3I, they invite a deeper, more unsettling line of questioning. The structured breakup theory, in its most extreme form, suggests that what we observed as fragmentation might actually have been a form of self-disassembly. Imagine a probe, a complex piece of machinery designed to separate into multiple, independent components upon reaching a target star system. Each component could carry its own set of sensors or instruments, and each could be programmed to follow its own trajectory to maximize the coverage and scientific return from the system. The breakup we witnessed might not have been a structural failure, but a deliberate, planned separation of modules. This theory, wild as it seems, could explain the linear pattern. If the components were connected along a central spine or within a frame, their separation would naturally produce a linear arrangement. It could explain the regular spacing. If the releases occurred at timed intervals, the spacing would directly reflect those intervals. It could even explain the directed plume. If one component retained an active propulsion system, its emission would appear as a persistent directional jet. The theory is wildly speculative, completely unsupported by any hard evidence, and is directly contradicted by the object's cometary appearance and behavior. K1 shows all the classic signs of being an icy body, not a metallic construct. Its spectrum reveals the presence of common volatiles. Its coma contains dust and gas that are entirely consistent with sublimating ice. If it is a probe, it is one that is perfectly disguised to look exactly like a comet, which in itself raises more questions than it answers. Why would an advanced civilization send probes across interstellar space, disguised as natural comets? Perhaps for stealth, to avoid detection by primitive civilizations like ours. Perhaps for efficiency, using naturally occurring materials as shielding or fuel. Or perhaps we are simply misunderstanding what we are seeing, interpreting artificial structures through the limited lens of natural processes because we lack the conceptual framework to recognize true artificiality. The Atlas naming coincidence also draws attention in these fringe circles. Both objects discovered by the same survey, both carrying the Atlas designation. This is of course purely a result of the survey's naming convention. Atlas discovers hundreds of objects each year, and all of them carry its name. But coincidence can feel deeply meaningful when the objects in question share such a profound list of unusual traits. Some fringe thinkers have even proposed that Atlas might be more than just a survey designation. Could it be a code, an identifier, something embedded in the objects themselves that triggers a specific response or detection by certain systems? This line of thought quickly veers into pure conspiracy territory, completely unsupported by any known mechanism or evidence, but it illustrates how speculation can spiral when anomalies multiply and conventional explanations feel increasingly strained. The self-replicating probe hypothesis adds another layer of complexity. Imagine von Neumann probes, self-replicating machines designed to explore the galaxy by using raw materials they find to create copies of themselves. Such probes might arrive in our solar system, appearing as unremarkable rubble piles, collections of components held together loosely, designed to separate and activate when the right conditions are met. K1's fragmentation could be interpreted as just such a separation, with modules breaking apart to begin their individual missions of exploration or replication. This idea requires technology far beyond our own, engineering at scales we can barely imagine, and motivations for a civilization that we cannot fathom. It is, for now, science fiction dressed in the language of astronomy. And yet, the question stubbornly persists. How would we recognize an artificial object if one entered our solar system, especially if it was disguised or camouflaged to look like a natural body? What specific observations would definitively distinguish a sophisticated probe from a comet? Most scientists rightly emphasize applying Occam's razor. The simplest explanation that fits the data is usually the correct one. K1's behavior, while unusual, can be explained by natural processes if we are willing to accept a specific, if somewhat unlikely, set of conditions. Invoking artificial origins adds immense complexity without adding any real explanatory power. The engineered hypothesis doesn't predict anything that the natural models cannot also predict. Counterpoints understandably dominate the scientific discussion. Veteran comet scientists warn strenuously against jumping to exotic conclusions when natural mechanisms, however poorly understood, still exist. The history of astronomy is filled with anomalies that seemed utterly inexplicable until better observations or improved theoretical models eventually resolved them. K1 will almost certainly follow this same pattern. What appears mysterious and provocative now will likely become mundane and understood once we have more data. But the thought experiment retains its value. What would we expect to see if one of these objects was engineered? We might expect motion anomalies consistent with a propulsion system. We might see directed plumes that resemble attitude control jets. We might witness fragmentation along clean geometric lines, like the separation of designed modules. We might find materials with isotopic ratios or elemental compositions that are impossible under natural conditions. We might see behaviors that seem to maximize information gathering or system coverage. K1, intriguingly, shows some of these traits in a muted, natural-seeming form. Whether they are hints of design or simply the outer limits of natural processes remains the critical, unanswered question. The fringe theories, for all their lack of evidence, serve a purpose beyond mere speculation. They push mainstream science to articulate its own assumptions more clearly, to explain precisely why natural explanations are more likely, and to gather the specific data that can distinguish between the possible and the impossible. The very existence of these exotic hypotheses motivates better observations, more careful analysis, and more rigorous testing of conventional models. K1 and 3i Atlas, whatever they ultimately prove to be, have already succeeded in expanding the conversation about what enters our solar system and why. They have forced us to confront the limits of our current knowledge and the gaps in our detection capabilities, and they have provided a powerful reminder that the universe is capable of producing phenomena that our current models have not anticipated, and that sometimes the most valuable scientific question we can ask is a simple, humble one. What if we're wrong? The fringe files do not provide any answers, but they ensure that we continue to ask the most profound questions. And as we now widen our lens once more to see the story of K1 in the context of other simultaneous breakthroughs from 2025, we will see that this theme of questioning our assumptions has become a recurring pattern across multiple, disparate fields of science. The universe, it seems, is not behaving as we expected, and K1 is just one particularly vivid example of a much broader and more exciting pattern. As the astronomical world was reeling from the implications of K1's fragmentation, another revolution was quietly unfolding in a different corner of space science, one that would challenge our assumptions just as profoundly. In November 2025, the James Webb Space Telescope delivered a set of findings that upended decades of established exoplanet atmospheric models with the same brutal efficiency that K1 had shattered our understanding of comets. The discovery centered on two super-Earths orbiting separate stars, worlds where the upper atmospheres were hotter than the layers beneath them, a phenomenon known as a thermal inversion. This simple fact, confirmed by repeated meticulous observations, was something that should not happen according to standard physics, yet the data was unequivocal. Planetary atmospheres, from Venus to Jupiter to the hot Jupiters we've studied for years, normally cool as you move upward from the heat of the surface or the interior. Temperature decreases with altitude until you reach the thin upper atmosphere, where intense stellar ultraviolet radiation can sometimes cause warming again, creating a complex profile. But a full, persistent thermal inversion flips this entire concept on its head. The upper atmosphere becomes a hot layer, with the cooler atmosphere trapped beneath it, a configuration that creates a temperature gradient opposite to everything our models predict for passive heating. On Earth, thermal inversions are temporary, localized events caused by specific weather conditions, trapping smog in valleys. On these two distant super-Earths, the inversions appeared to be permanent, global, and stable, affecting the entire climate system of the planet. JWST's powerful spectrographs detected these inversions by analysing the starlight that filtered through the planet's atmospheres during their transits. Different molecules absorb light at specific wavelengths, and the strength of that absorption is exquisitely sensitive to temperature. By dissecting the resulting spectrum, astronomers could reconstruct the temperature structure of the atmosphere layer by layer. For HD 189733b and K2 417b, the data revealed absorption patterns that were consistent with only one possible conclusion: the temperature was increasing with altitude. What could cause such a bizarre and persistent phenomenon? One leading hypothesis points to extreme stellar activity. If the host stars are prone to intense flaring or emit unusually high levels of ultraviolet radiation, that energy could heat the upper atmosphere far more efficiently than the infrared radiation can heat the lower layers. These planets orbit perilously close to their stars, with years lasting only a few Earth days, bathing them in an unrelenting torrent of radiation. Another possibility involves exotic atmospheric chemistry. If the upper atmosphere is rich with molecules that have unusual optical properties, materials that absorb visible or ultraviolet light with incredible efficiency and convert it directly into heat, they could act as a kind of celestial blanket, trapping heat at high altitude. On Earth, ozone creates a mild inversion in the stratosphere through UV absorption. These exoplanets might possess a much more potent and extreme version of this process. A third theory suggests high metallicity. If these atmospheres are enriched with heavy elements far beyond what we see in our solar system, the increased opacity and heat capacity could trap thermal energy more effectively in the upper layers, creating the inverted profile. Computer models show that metal-rich atmospheres under intense stellar radiation can develop complex and counterintuitive temperature structures, including these stable inversions. The parallel to the K1 mystery is conceptual but powerful. Just as K1's behavior exists outside the standard templates for comets, these atmospheric inversions exist outside the standard templates for planetary climates. Both discoveries are stark reminders that the universe does not feel obligated to follow the rules we have derived from studying our own limited cosmic backyard. Other star systems can produce planets with atmospheres unlike anything orbiting our Sun, just as they can produce small bodies with compositions and behaviors unlike our native comets and asteroids. The specific planets, HD 189733b and K2-417b, are not habitable worlds. They are super-Earths, with masses several times that of our own planet, orbiting so close to their host stars that their dayside temperatures exceed 1000 Kelvin. They are, however, perfect natural laboratories for studying atmospheric physics under the most extreme conditions imaginable. JWST's observations included multiple transits for each planet, repeated measurements that confirmed the inversions were not a fluke, but a real, stable feature of these alien worlds. The data also revealed other chemical surprises. Water vapor concentrations were lower than predicted, carbon dioxide levels were higher, and there were tantalizing hints of molecules not previously detected in any exoplanet atmosphere. The chemistry, like the temperature structure, defied simple textbook explanation. Atmospheric scientists are now in a race to revise their models to account for these observations. The inversions might in fact be common among hot super-Earths, but remained invisible to us until JWST's unprecedented sensitivity brought them into sharp focus. The same technological leap that is revealing the strangeness of K1 is revealing the strangeness of worlds light years away. The theme emerging from 2025 is one of humbling discovery. Every major finding of the year has revealed phenomena that lie outside our expectations. Exoplanet atmospheres don't behave as predicted. Comets fragment in organized, inexplicable patterns. Interstellar objects arrive with alien chemistries. The cosmos is proving to be more diverse, more complex, and more surprising than our theories have allowed for. This doesn't mean our theories are wrong. It means they are incomplete. We built our models based on the examples we could most easily study: the planets in our solar system, the comets from our Oort cloud, the stars in our immediate galactic neighborhood. Those models work beautifully for objects that are similar to our references. But when we finally gain the ability to study objects from different environments, formed under different conditions, existing in different physical regimes, the models inevitably begin to break down at the edges. K1's story intersects with the exoplanet atmospheric reversals at this philosophical level. Both discoveries force us to expand our understanding, to acknowledge that nature's creativity far exceeds our own imagination. Both remind us that anomalies are not nuisances to be explained away, but precious opportunities to learn something fundamentally new. And both demonstrate that our most sophisticated instruments have finally reached a point where they can reveal just how much we still have left to learn. The November 2025 JWST findings are still filtering through the scientific community. Papers are being written, models are being torn down and rebuilt, and passionate debates are ongoing. But the impact is already irreversible. Atmospheric science will never be quite the same, just as comet science has been irrevocably altered by K1. We are living through a period of rapid, disorienting discovery, where our tools have finally caught up to phenomena that have existed all along, hidden in plain sight. And this theme of unexpected revelation, as we are about to see, extends even to the practical, gritty work of preparing our next robotic explorers to meet these mysteries head-on. While telescopes were tracking K1's fragments and JWST was rewriting textbooks on exoplanets, on the ground, engineers for the European Space Agency's Comet Interceptor mission were facing their own, more immediate puzzle. The mission represents a bold new step in exploring our solar system's most enigmatic visitors. Unlike previous missions like Rosetta that targeted known short-period comets, the Comet Interceptor is designed to launch and then wait in a parking orbit, ready to be swiftly redirected toward a newly discovered, pristine long-period comet, or, ideally, the Holy Grail, an interstellar object. When 3I Atlas was discovered, mission planners briefly and excitedly assessed it as a target before the harsh realities of orbital mechanics and timeline made the idea impossible. But in late 2025, during critical pre-flight calibration of the spacecraft's dust analyzer instruments, the team encountered readings that didn't match their predictions. The sensors, designed to measure the density and composition of dust particles in a comet's coma, were responding to calibration dust clouds with signals indicating particle densities 3 to 5 times higher than the test setup should have produced. Repeated tests showed the same consistent anomalies, suggesting either a fundamental miscalibration of the instruments or, more intriguingly, a fundamental misunderstanding of how cometary dust actually behaves. The dust analyzer works by measuring the impacts of individual particles as the spacecraft flies at high speed through a comet's coma. Each impact produces a signal whose strength and signature indicate the particle's size, speed, and composition. During calibration, engineers generate artificial dust clouds with precisely known properties to verify the instrument's response is accurate. The anomalies appeared when using dust analogues specifically designed to mimic the expected composition of cometary material. Either the calibration clouds were somehow much denser than intended, the instrument was wildly oversensitive, or the dust particles were behaving in unexpected ways that amplified their signal. Subsequent, painstaking analysis ruled out simple instrument error. Multiple, identical sensors all showed the same anomalous response. The problem wasn't in the hardware, it was in the assumptions. Cometary dust is notoriously complex. The particles are not solid little spheres, they are a menagerie of submicron grains to pebble-sized chunks, composed of silicates, complex organics, and ices mixed in ratios that vary dramatically from one comet to another, and even within different regions of a single comet's coma. Critically, the particles are often fluffy aggregates, extremely porous, fractal-like structures rather than solid grains. This fluffiness gives them unexpected aerodynamic and electromagnetic properties, affecting how they scatter light, how they impact a sensor, and how they are pushed by solar radiation. Previous missions to comets like 67P Churyumov-Gerasimenko revealed dust behavior that consistently surprised scientists. The interceptor's calibration anomalies were a stark warning that more surprises were in store. The relevance to K1 becomes immediately clear when you consider what these anomalies imply. If cometary dust is consistently denser or behaves in more complex ways than our models predict, then our remote observations of objects like K1 could be systematically misinterpreted. The brightness of K1's coma, which we use to estimate its mass loss rate, could be indicating far more material than we think, or a different distribution of particle sizes, or compositional variations we aren't accounting for. Those plumes and jets, so critical to understanding its motion, might be carrying a different payload of material than our spectroscopic measurements suggest. K1's golden hue and its unusual dust-to-gas ratio were already flags that something was odd about its particle properties. If dust in general behaves in more complex and varied ways than our standard models assume, then K1's behavior becomes less of a shocking anomaly and more a representative of a diversity we simply haven't mapped yet. The interceptor calibration issues provide independent, ground-based evidence that cometary dust science is still in its infancy, with significant gaps in our understanding. Mission planners now face difficult decisions. Do they adjust the instrument's sensitivity, revise the calibration procedures, or simply accept that the sensors will encounter dust environments more extreme and variable than anyone anticipated? The choice is critical because the comet interceptor might be humanity's first chance to have a close encounter with a confirmed interstellar object. If such objects produce dust clouds that are denser, stranger, or more aggressive than those of normal solar system comets, the spacecraft needs to be prepared for that reality. The pre-calibration anomalies, in a way, validate the very existence of the mission. If comets and interstellar visitors were fully understood, if our models were complete, there would be far less scientific justification for a risky, expensive intercept mission. The anomalies prove that remote observations, no matter how sophisticated, can never replace the raw, tactile data of in situ measurement. We need a spacecraft to physically fly through these environments, to taste the dust, to measure the magnetic fields, and to report back what our telescopes, for all their power, cannot see. K1 is a powerful preview of what the comet interceptor might one day encounter. If K1 is indeed an interstellar fragment, its dust properties could be a direct analogue to what 3I Atlas produced and what future interstellar visitors will produce. The organised fragmentation, the persistent plume, the unusual chemistry, all of it points to dust behaviour that exists outside our current comfort zone. The interceptor's instruments, if properly calibrated for such an exotic environment, could finally provide the definitive answers that are currently eluding us. The timing is fortuitous. The comet interceptor is scheduled to launch in 2029, reach its parking orbit at the Earth-Sun L2 point, and wait. With the rate of interstellar object detection seemingly increasing, 3 confirmed in less than a decade compared to 0 before 2017, there is a reasonable probability that a suitable, pristine target will appear during the mission's operational lifetime. K1 and 3I Atlas have demonstrated that interesting objects are arriving with a frequency that justifies the gamble of a waiting game. Scientists at the European Space Agency are now actively incorporating the lessons from K1 into their mission planning. They are updating dust environment models, revising risk assessments for the spacecraft's shielding, and considering what instrumentation might need adjustment based on what K1 has revealed. The fragmentation event, in particular, provides a treasure trove of data on how cometary nuclei can disintegrate, information that is absolutely critical for planning safe flyby distances and timing. The calibration anomalies serve as a crucial reminder that every space mission we send beyond Earth encounters the unexpected. Every probe reveals phenomena that our models failed to predict. The anomalies don't indicate failure, they indicate the frontier of knowledge, the precise edge where our theoretical understanding meets reality, and reality, as it always does, wins. K1, with its cascade of anomalies, represents that frontier in the realm of small solar system bodies. As the comet interceptor prepares for its eventual launch, and as astronomers continue to track the fading fragments of K1, the connection between the two grows stronger. One is an observation, a mystery awaiting an explanation. The other is an explanation, a mission awaiting its mystery. Together, They represent humanity's evolving, maturing capability to study the small bodies that populate our cosmic neighborhood and that visit from the great beyond. And both remind us, with thrilling clarity, that the universe is still rich with surprises, waiting just beyond the next launch window. From the cosmic drama of fragmenting comets and inverted atmospheres, in a laboratory buried deep beneath the Italian Alps to shield it from any interference, a team of physicists in 2025 detected a signal that, according to our current understanding of the universe, should not exist. An exquisitely sensitive experiment designed to test quantum gravity effects at microscopic scales returned a persistent, non-zero measurement. It was a tiny deviation, barely peaking above the experimental uncertainty, but it was there, and it suggested that gravity behaves differently at the quantum scale than Einstein's theory of general relativity predicts. The experiment involved cooling atoms to near absolute zero, trapping them in grids of laser light known as optical lattices, and manipulating them with a precision that borders on the magical. The goal was to observe whether quantum superposition states, the bizarre ability of particles to exist in multiple states at once, experience a unique form of decoherence caused by gravity itself. The question at the heart of it is one of the biggest in all of physics. Does gravity have quantum properties? Standard quantum mechanics describes a world of probabilities and superpositions, where particles are fuzzy clouds of possibility until measured. General relativity describes gravity as the smooth, classical curvature of a four-dimensional spacetime. The two theories are brilliant, powerful, and fundamentally incompatible. Combining them produces mathematical nonsense at the extreme scales of the Big Bang or the center of a black hole. Physicists have proposed numerous theories of quantum gravity to bridge this chasm, but experimental tests have been nearly impossible because gravity is astronomically weaker than the other fundamental forces at the small scales where quantum effects dominate. The Italian experiment represents years of relentless refinement, pushing the precision of measurement to a regime where the faintest whispers of quantum gravitational effects might finally be heard. The non-zero signal appeared in the measured rates of decoherence. Quantum superpositions naturally and inevitably decay into definite states through interactions with their environment. This is the process of decoherence. The rate of this decay depends on many factors, but according to standard theory, gravity's contribution should be vanishingly small, effectively zero. The measured decay rates in the experiment, however, consistently exceeded predictions by a tiny, almost insignificant margin. The particles in their delicate superpositions were collapsing into a single state just slightly faster than they should have, as if gravity itself was contributing a small but measurable push toward decoherence. The effect is minuscule, requiring months of data collection and averaging to even be visible, but it is persistent and, so far, reproducible. Multiple runs of the complex experiment have all shown the same excess decoherence. If this finding is confirmed by independent experiments in other laboratories around the world, it would represent the first ever empirical evidence that gravity operates differently at the quantum scale, that space-time itself might have a granular, quantum foam-like structure that affects the behavior of the particles moving through it. The implications would cascade through all of physics, touching everything from black hole thermodynamics and the fate of information within them, to cosmology and the very first moments of the universe, to the fundamental nature of reality itself. The connection to K1 and the other astronomical anomalies of 2025 is not direct, but it is philosophically profound. We are not suggesting that quantum gravity explains why comets fragment in lines, or why exoplanet atmospheres invert. The parallel is in the pattern. In multiple, disconnected domains, from laboratory physics to exoplanet atmospheres, to the behavior of small, icy bodies, the year 2025 has been marked by phenomena that refuse to conform to the predictions of our established models. Reality is pushing back, showing us the boundaries of our knowledge in field after field. Quantum gravity effects, if they are real, could one day be found to influence astrophysical processes in ways we haven't yet dreamed of. The interiors of neutron stars, the event horizons of black holes, the seething vacuum of the early universe. All are environments where quantum effects and gravitational effects are both immensely powerful. Understanding how gravity truly behaves at its most fundamental level could force a revision of our understanding of these cosmic extremes. Similarly, understanding how small bodies like K1 actually work forces a revision of our understanding of planetary system formation and the distribution of matter in the galaxy. The Italian experiment's results remain preliminary. The signal is faint, and the world of physics is rightly skeptical. Other laboratories are now preparing their own, even more sensitive experiments to attempt replication. Theoretical physicists are exploring whether the observed signal could come from other, more mundane sources of decoherence that haven't been fully accounted for. The scientific process, slow and rigorous, is in motion. Anomalous results trigger skepticism and further testing, not immediate celebration. But the mere existence of a plausible quantum gravity signal has sent a jolt of energy through the field. For decades, quantum gravity has been a purely theoretical playground, a realm of untestable speculation about physics at scales too small and energies too high for any experiment to probe. If tabletop experiments using ultra-cold atoms and laser interferometry can truly access these effects, then a whole new era of experimental fundamental physics is dawning. Laboratories could begin to test the predictions of string theory, loop quantum gravity, and other candidates, guiding theoretical development with hard, empirical data for the first time. K1's anomalies and the quantum gravity signal share this transformative characteristic. Both represent phenomena at the very edge of our observational and theoretical reach. Both challenge the models we have grown comfortable with. Both are invitations to investigate more deeply, to question more fundamentally. They are reminders that science does not advance through the steady confirmation of what we already believe, but through the startling discovery of what we never expected. The year 2025 is shaping up as a period when multiple scientific fields are simultaneously confronting their own limitations. It is not that our theories were wrong, it is that they were incomplete, built on a limited set of examples and tested only in the regimes that were historically accessible. As our instruments improve, whether they are space telescopes, sky surveys, or tabletop quantum experiments, and as our observations extend into these new territories, the incompleteness of our understanding becomes visible and the path forward is illuminated. Quantum gravity research and small body astronomy might seem worlds apart, but they are connected by methodology and a shared philosophy. Both fields push measurement technology to its absolute limits. Both deal with phenomena that are too small, too fast, too distant, or too weak for easy observation. Both require painstaking, careful analysis to distinguish a true signal from the ever-present background noise. And both now face the exhilarating challenge of interpreting anomalous data when the very theories that might explain it are themselves uncertain and in flux. The Italian experiment will continue, taking more data, refining its measurements, testing alternative explanations. Independent labs will spend years on their own attempts at replication. Theoretical work will explore the implications and develop new, testable predictions. The process will be long, and the final conclusion is unknown. But the existence of that tiny, non-zero signal, however tentative, has already irrevocably changed the conversation in physics. Meanwhile, K1's fragments continue their journey into the outer darkness, still tracked by telescopes, their path still being refined, their light slowly fading. The data continues to accumulate, the uncertainties slowly narrow, and the picture of what happened that November gradually becomes clearer. Both the quantum experiment and the comet observations are science at its purest and most exciting, measuring with care, questioning with depth, and remaining humbly, passionately open to the possibility that reality is, and always will be, stranger than our very best theories suggest. In a world increasingly driven by data, it was perhaps inevitable that artificial intelligence would find its way to the stars. In 2025, a research team unveiled a neural network that had been trained on the light curves of thousands of comets, a system capable of forecasting fragmentation and outburst events weeks before they occurred. Its name was Celestial Forecaster, and its first major public success was a prediction that seemed to border on prescience. It flagged C 2025 K1 Atlas as having a high risk of fragmentation a full 3 weeks before the comet tore itself apart in November. The AI system uses a deep learning architecture to identify subtle, complex patterns in how a comet's brightness changes over time, its light curve. As a comet approaches the Sun, rotates and outgasses, its brightness flickers and flares in a unique signature. Experienced astronomers can sometimes recognize the warning signs of an impending fragmentation, a sudden, irregular brightening, a change in the periodicity of the light curve, an unexpected outburst. But human pattern recognition has its limits, and rare events are difficult to predict without a vast reservoir of subconscious experience. Machine learning, however, excels at this exact task. The research team compiled a massive database of light curves from thousands of comets, spanning decades of observations. They then labeled this data based on what happened afterward. Did the comet fragment? Did it remain stable? Did it have a major outburst? They then trained their neural networks to recognize the precursor patterns, the specific features in the light curves that correlated with these later dramatic events. The resulting model could analyze the ongoing observations of a new comet and output a simple, terrifying number, a fragmentation probability, a percentage likelihood that the object would break apart within a specified time window. For the vast majority of comets, this probability remained low throughout their passage. For a select few, the model would flag an elevated risk, based on features in their light curves that resembled the historical cases of fragmentation. In late October 2025, Celestial Forecaster analyzed the growing light curve data for K1 Atlas and assigned it a 73% probability of fragmentation within the next 30 days. The model had identified specific irregularities in the brightness variations and spin state indicators that matched the patterns it had learned were precursors to catastrophe. The team issued an alert to the astronomical community, recommending increased observational coverage. Not everyone took the AI's warning seriously. AI predictions in astronomy had a mixed track record, with some models producing dramatic false alarms or missing real events entirely. Veteran comet observers noted that while K1's light curve was somewhat irregular, it wasn't obviously pathological. Many comets show brightness variations without ever coming apart. A 73% probability still meant a more than 1 in 4 chance that nothing would happen. Then, on November 12th, it happened. K1 fragmented, exactly as the model had forecast. The multiple telescopes that had been pointed at it based on the alert captured the event in stunning detail, vindicating the AI's cold, statistical prediction, and demonstrating that machine learning could identify precursor signatures that were completely invisible to even the most experienced human eye. The success doesn't mean the model is perfect, but it validates the entire approach. AI can extract predictive information from vast streams of observational data that traditional analysis simply misses. How does it work? The neural network isn't a physicist. It doesn't understand thermal stress or structural mechanics. It is a pattern recognition engine. Its convolutional layers process the light curve time series, its recurrent layers capture temporal dependencies, and its attention mechanisms identify which specific features matter most for the prediction. During its training, it learned that certain combinations of brightness variation, periodicity changes, and color shifts correlate with a high probability of future fragmentation. When it sees a new light curve that looks like that, it raises a flag. This black box nature troubles some astronomers, who prefer physically motivated models where predictions are tied to understood mechanisms. But pragmatically, if the AI predicts accurately, the lack of easy interpretability becomes a secondary concern. Celestial Forecaster has now been set to work on K1's own fragments, analysing their post-breakup light curves to predict whether they will fragment further. Early results suggest the leading fragment, the one with the persistent bright plume, has an elevated risk for additional breakup, while the other fragments appear more stable. Observers are now targeting this high-risk fragment with intense monitoring, a real-time test of the AI's continuing predictive power. The model's success raises a profound question. What else might be predictable? Could AI forecast comet outbursts? Could it identify which near-Earth asteroids are most likely to break apart during a close pass? Could it even flag highly unusual objects like 3I/Atlas before they are formally confirmed, based solely on the strangeness of their light curves? Early tests suggest the answer is yes. The model has successfully identified other objects with anomalous light curves, helping to prioritize precious telescope time for follow-up observations. K1's prediction was not its only success in 2025. It also correctly forecast 2 smaller comet fragmentations and identified 3 other objects with such unusual behavior that they warranted detailed study. It has produced its share of false alarms too. Several comets flagged as high risk have remained stubbornly intact. The false positive rate needs improvement, but the fact that it catches real events at all demonstrates a powerful potential. The philosophical implication is fascinating. If an AI can predict fragmentation, it means the precursor signatures were always there, embedded in the observational data, waiting to be recognized. Human astronomers were missing them not because they weren't present, but because pattern recognition in noisy, high-dimensional data is an inherently difficult task for the human brain. The machine succeeds where we fail, not through understanding, but through the brute force statistical analysis of thousands of examples. This doesn't diminish the achievement. Medicine uses AI to detect diseases from medical images. Finance uses it to predict market movements. And now, astronomy is using it to forecast celestial events. The tool augments human capability, handling the tasks we are poorly suited for, while leaving the final interpretation, the physical insight, and the wonder to the scientists who provide the context. K1's story intersects with AI forecasting at the most practical level. The successful prediction meant that when the fragmentation occurred, the world's telescopes were already watching. The event was documented with a density and quality of data that would have been impossible otherwise. As the model continues its development, researchers are expanding its training data to include more recent observations and are incorporating multi-wavelength information, infrared data, spectroscopy, polarimetry, which may provide even greater predictive power. The goal is a comprehensive, automated system that monitors all known small bodies and flags anything unusual for human attention, ensuring we never miss another cosmic breakup. The success of Celestial Forecaster represents a fundamental shift in how astronomy will be done. Increasingly, AI systems will perform the initial, data-intensive sifting, identifying the most interesting and anomalous cases, and directing limited human attention to where it is most needed. We are moving toward a hybrid future, where machines handle the vast, tedious work of pattern recognition across enormous datasets, and humans provide the creativity, the context, and the deep physical intuition. K1's predicted fragmentation is a powerful proof of concept for this hybrid approach, catching a dramatic event that might otherwise have been a total surprise. It is a sign that our eyes on the sky are becoming smarter, more vigilant, and more capable of seeing the unexpected before it even happens. Step back. Survey the entire landscape of astronomy in this remarkable year. Look at the pattern emerging from seemingly disconnected fields, the common thread running through quantum labs, exoplanet atmospheres, and fragmented comets. 2025 has been a year when the objects of our study, from the subatomic to the galactic, have collectively refused to behave according to our models. It has been a year when anomalies have accumulated faster than our theories could assimilate them, a year of profound and humbling discovery. Start with the interstellar visitors. 3I Atlas arrived in July, a confirmed stranger from another star, with chemistry and polarization that marked it as utterly alien to our solar system. Then K1 Atlas fragmented in November, a supposed native comet that acted nothing like one, showing organized disintegration, unexplained motion, and a bizarre chemical signature. Both carried the same name, both appeared within months, and both raised the chilling possibility that our solar system is being visited by interstellar material far more often and in far more complex ways than we ever imagined. Move to the worlds around other stars. The James Webb Space Telescope revealed thermal inversions in the atmospheres of 2 super-Earths, turning standard atmospheric models on their head. The discovery suggested either exotic chemistry, extreme stellar environments, or atmospheric dynamics so complex we have yet to even conceive of them. It forced a revision of models that had worked perfectly well for the planets in our own solar system, but failed when applied to these distant cousins. Shift to the realm of fundamental physics. In a laboratory under a mountain, a quantum gravity experiment recorded a tiny, persistent signal that hints at a quantum structure to space-time itself. If confirmed, it would be the first empirical step into a theoretical domain that has been closed to experiment for a century, opening new windows into the nature of black holes, the Big Bang, and reality itself. Consider the tools and the missions. The Comet Interceptor's pre-calibration anomalies revealed that we still don't fully understand the dust environment of the very objects we plan to visit. And the artificial intelligence system that successfully predicted K1's breakup demonstrated that machine learning can see patterns in the sky that are invisible to us, heralding a new era of hybrid, AI-assisted discovery. The list extends further. Unexplained stellar dimming events, strange X-ray echoes from the galactic center, a neutrino burst that arrived out of sync with its associated gamma-ray signal. Each of these, alone, could be an instrument glitch or a rare fluctuation, but together they form a pattern. Across the board, from the smallest scales to the largest, 2025 has been the year the universe demonstrated, with quiet insistence, that our understanding is incomplete, that nature's diversity exceeds the boundaries of our current theories, that the next great surprise is always waiting, just beyond the edge of our current vision. K1 and 3I Atlas are the exemplars of this theme in small body science. For decades, we built our models of comets and asteroids based on the objects from our own solar system. The occasional oddball could be dismissed as an outlier. Now, with interstellar objects being detected with increasing frequency, and our surveys becoming sensitive enough to see the fine details of fragmentation, we are encountering small bodies that simply do not fit the old categories. The philosophical question is whether we are discovering new types of objects or simply seeing the true, full diversity that has always been there. Are K1 and 3I genuinely unusual, or are they perfectly normal examples of populations from interstellar space, or from the far, uncharted reaches of our own Oort cloud that we have never properly sampled before? The answer likely lies in the middle. These objects are unusual by the parochial standards of our inner solar system, but they may be utterly typical of the wider galaxy. The year's discoveries share powerful methodological lessons. First, we must always expect the unexpected. When our instruments finally achieve the sensitivity to detect subtle effects, they often reveal phenomena that no theory predicted. Second, anomalies are not failures. They are the most valuable opportunities we have to learn. Every observation that contradicts a model is a chance to expand our understanding. Third, interdisciplinary thinking is no longer a luxury, it is a necessity. K1's story connects to exoplanet science, to AI development, to fundamental physics, and to spacecraft engineering. The next breakthrough will likely come from recognizing a pattern that connects these seemingly separate fields. The accumulation of anomalies in 2025 might seem disorienting, as if the scientific edifice is cracking. In reality, it is a sign that science is working exactly as it should. Our instruments have finally become good enough to test our theories in the regimes where they are most vulnerable. Our surveys are deep enough to catch the rare events. Our models are precise enough that the deviations are now obvious. We are not losing our understanding. We are gaining a new, more nuanced, and more accurate awareness of just how much we have left to explore. K1's fragments continue to drift apart, their paths still tracked, their light slowly fading as they journey back toward the outer darkness. 3I Atlas is now far beyond Jupiter, a fading speck on a one-way trip back to the interstellar void. The exoplanets with inverted atmospheres continue their endless, scorching orbits, untouched by our detection of their strangeness. The quantum gravity signal persists in the Italian data, awaiting confirmation or refutation. None of these mysteries will be resolved quickly. K1's origin may remain ambiguous for years until additional fragments are found or better orbital data clarifies its past. The atmospheric inversions will require more JWST time, more complex models, and possibly decades of work to fully understand. The quantum gravity signal needs replication across the globe before the physics community will accept it. But the uncertainty is not frustrating. It is the most exciting place to be. We are living in an era when major discoveries are no longer rare, when each observing season brings new surprises, when our technology has finally risen to meet our ambition. The questions we are asking now: how common are interstellar objects? How diverse are planetary atmospheres? Does gravity have quantum properties? Can we predict the heavens? Will occupy scientists for generations. The story of K1 Atlas is not finished. Its fragments will be tracked until they fade from view. Future observations might reveal more pieces of the puzzle in archival data or connect it to other strange objects. The narrative will evolve, but the bigger picture is now clear. 2025 taught us that the universe is more complex and wonderful than our solar system-centric models allowed. That small bodies come in varieties we are only beginning to catalogue. That interstellar space contributes actively and constantly to our local environment, and that every answered question reveals a dozen new, more profound mysteries. We stand at the edge of a new understanding, looking out at a cosmos that delights in refusing to be fully known. So, what else is on its way? What other fragments are drifting through the darkness between the stars, silent and dark, on a course that will eventually bring them through our neighbourhood? What other unusual objects are hiding in the terabytes of survey data, waiting for an AI or a curious human to recognise their strangeness? What other atmospheric inversions, quantum signals, or organised breakups will the next year bring? The sky is not a static picture. It is a dynamic, evolving story. It holds the answers to questions we haven't even learned to ask yet. Our telescopes are scanning, our instruments are measuring, our computers are analysing. And somewhere out there, right now, another object is inbound, carrying its own unique mysteries, ready to challenge everything we think we know. Keep looking up. Stay curious. The universe has only just begun to surprise us.